today we'll be talking about global state. Another common reason for performance issue is how components are dependent on the application global state. The worst case scenario is when the state changes of a single control like text input or checkbox propagates the render of the whole application. The reason for this is a bad global state management design. We recommend you use specialized libraries like Redux or Overmind.js to handle your management in a more optimized way. First, your state management library should take care of updating component only when subset of data has changed. This is the default behavior of the Redux connect function. Secondly, if your component uses data in a different shape than what is stored in your state, it may if your component uses data in a different shape than what is stored in your state, it may re-render even if there is no real data change. To avoid this situation, you can implement a selector that would memorize the result of the derivation until set of past dependencies changes. Okay, reselect, create selector, a common bad performance practice is a belief that state management library can be replaced by custom implementation based on React context. It may be handy at the beginning because it reduces the boilerplate the state management library introduced, but using it without proper memoization will lead to huge performance drawback. You probably end up refactoring state management to Redux because it will turn out that it is easier to implement than the implementation of custom selectors to your current solution. You can also optimize your application on a single component level. You using react.memo or react.useMemo will likely save you a lot of re-renders. The React profiler can tell you precisely how many. Try not to implement these techniques in advance because it may be premature optimization. In rare cases, memoization can lead to the app being less performant due to increased memory usage, which is possible to measure with JS tooling. Always make sure to profile the before and after of your changes to have certainty. It make the app faster. Atomic state the pattern of a single store. A top-down mental model as initially promoted by Redux is moving towards a more atomic design. Why is it moving away from a single store? It is often overkill for some apps. It is too verbose. You end up using memoization techniques to avoid re-render. Top-down is straightforward but leads to poor performance. More states are needed when the apps grow, and each has its own problem and subsets such as handling local UI states, loading error messages, etc. If you don't pay attention to Redux, it tends to absorb all the state, leading to a monolithic structure that's quite hard to reason with. The top-down build places most of the states at the top of the component. Because of this, a state update from parent component could produce re-rendered state shell. Ideally, if possible, the state should be local to the component so it cannot be reused. This means building from the bottom up. To start thinking about this bottom up pattern, we want to build from smaller components, often called atoms. We don't want the component starting from parent or root container component element. We need to look at all the elements that make up the component. We then have to start from the atom and add the right state action if needed. Let's say we have a to-do list with some filters: show all, just the active ones, or just the complete. We identify the top component to-do list, but we don't start here. We first identify the children and start building those smaller components so that later we can mix them and build a complex element. We need to make some data visible in one component which will be managed by another one. To avoid a parent state and passing down the data and action top down, we are going to use a state manager. This state manager will be in charge of storing the data, making it accessible and performing actions modifier. Because we are Moving to a bottom-up approach, we are going to use some libraries that will help us. The stand is often used as a top-down pattern, but given the simplicity and unopinionated library, we can use it to build the component bottom-up. We create the object where the filter will be and the modifiers will be exposed. Show all filter button. To do item. Jotai was built with this bottom-up approach in mind, so its syntax is minimal and simple, using the concept of atom as a store. Then you can use different hooks to make them atom readable, read-only or mutable. We use atom value to read the filter value and use set atom to set a new value. This is especially useful when performance is a concern. Filter menu item. To do item. To do item list, sorry. Using this bottom-up approach, we can prevent state changes on the parent component and produce re-render to its child. In addition, it often leads to less overuse of memoization, benefits fewer resources needed, and a faster application. You should always keep the performance of your app in the back of your head. Be aware of optimizing too fast. Some say that premature optimization is root of all evil. They are not entirely correct, but also not entirely wrong. Premature memoization may lead to more memory usage and provide only a fraction of improvement compared to the effort taken. That's why measuring and identifying impactful problems to tackle is so important. Most hard solved problems issues are caused by bad architecture decision around state management. Different libraries juggle different sets of trade-offs. Make sure you and your team understand them and pick the tool you are most productive with. For example, it may be the verbosity of Redux, but other may prefer the ease of Zustand that avoids having to think about extra re-renders. With all these steps in mind, your application should perform fewer operations and need smaller resources to complete its job. As a result, this should lead to lower battery usage and more satisfaction from interacting with the interface. Use dedicated components for certain layouts. Find out how to use higher order React Native component to improve the user experience and performance of your app. Issues you are unaware of the higher order components that are provided with React Native. In a React Native application, everything is a component at the end of the component hierarchy. These are so-called primitive components such as text view or text input. These components are implemented by React Native and provided by the platform you are targeting to support the most basic user interaction. When we are building our application, we compose it out of smaller building blocks. To do so, we use primitive components. For example, in order to create a login screen, we should use a series of text input component to register user details and a touchable component to handle user interaction. This approach is true from the very first component that we create within our application and holds true through the final stages of its development. On top of primitive component, React Native ships with a set of higher order components that are designed and optimized to serve a certain purpose. Being unaware of them or not using them can potentially affect your application performance, especially as you populate your state with real production data. Bad performance of your app may seriously harm the user experience. In consequences, it can make your clients unsatisfied with your product and turn them towards your competitors. Not using specialized component will affect your performance and UX as your data grows. If you are not using specialized components, you are opting out of performance improvements and risking a degraded user experience when your application enters production. It is worth noting that certain issues remains unnoticed while the application is developed, as mock data is usually small and doesn't reflect the size of a production database. specialized components are more comprehensive and have a broader API to cover them than the vast majority of mobile scenario solutions. Always use a specialized example flat list for list. Let's take long list as an example. Every application contains a list at some point. The fastest and dirtiest way is to create a list of items would be combine scroll view and view primitive components. However, such an example would quickly become problematic when the data grows. Dealing with large data sets, infinite scrolling, and memory management was the motivation behind Flatlist, a dedicated component in React Native for display and working with data structure like this. Compare the performance of adding a new list element based on scroll view to a list based on flat list. The difference is significant, isn't it? In the provided example of 5000 list item, the scroll view version does not even scroll smoothly at the end of the day. Flatlist uses scroll view and view components as well. What's the deal then? Well, the key lies in the logic that is abstracted away within the flatlist component. It contains a lot of heuristic and advanced JavaScript calculation to reduce the amount of extraneous renderings that will happen when you are displaying the data on screen, and to make the scrolling experience always run at 60 fps. Just using flatlist may not be enough. In some cases, flatlist performance optimization rely on not rendering elements that are currently not displayed on the screen. The most costly part of process is layout measuring. Flatlist has to measure your layout to determine how much space in the scroll area should be reserved for upcoming elements. For example, complex list elements, it may slow down the interaction with flatlist significantly. Every time flatlist approaches to render the next batch of data, it will have to wait for all new items to render to measure that. However, you can implement get item height to define the element height up upfront without the need for measurement. It is not straightforward for items without a constant height. You can calculate the value based on the number of lines of text and other layout constraints. We recommend using the React Native text size library to calculate the height of displayed text for all list items at once. In our case, it significantly improves the responsiveness for scroll elements of flat list on Android. Flashlist as a successor to Flatlist, as already discussed, Flashlist drastically improves the performance of uselist compared to scroll view. Despite proving itself as a performance solution, it has some caveats. There are popular cases where developers or users have encountered where, for instance, blank spaces while scrolling, lagging scrolling, and a list not being snappy almost on a daily basis. Flatlist is designed to keep certain elements in memory, which adds overhead on the device and eventually slows the list down, and blank areas happen when flatlist fails to render the items fast enough. We can, however, minimize the performance to some extent by following the tips here, but still, in most cases, we want um, smoothness and snappy list. With flat list, the JS thread is busy most of the time, and we are always fancy having 60 fps tags associated with our JS thread when we are scrolling the list. So how should we approach such issue? If not flat list, then what? Luckily for us, the flow folks at Shopify develops a pretty good drop-in replacement for flat list known as flash list. The library works on top of recycler list view, leveraging its recycling capability and fixing the common pain points such as complicated API using cells with dynamic heights or first render layout inconsistency. Flashlist recycles the items that are outside of the viewport and reuses them for other items. If the list has different items, Flashlist uses a recycle pool to use the item based on its type. It's crucial to keep the list items as right as possible without having any side effects. Otherwise, it will hurt the performance of the list. There are a couple of props that are quite important with flash list. First is estimated item size, the approximate size of the list item. It helps flash list to dedicate how many items to render before the initial load, and while scrolling, if we have different size item, we can average them. We can get this value in a warning by the list. If we do not supply it on the first render and then use it forward, the other way is to use the element inspector from the dev support in the React Native app. The second prop is override. So the problem with using flashlist is that it still does not support React Native's new architecture. That's why I'm not really interested in flashlist for now, but maybe 2-3 years down the line, if we support a new React Native's new architecture, and if flatlist is still slow in my case, then I might go with flashlist. But for now, I'm not really interested in flashlist. We can also use BAMLabs Android Performance Profiler, which gives us the result for FPS on the release build in the form of a performance report. It also creates a nice looking graph of CPU usage over the period of profiling, so we can vary how certain actions affect this metric. There's also React Native Performance Monitor Flipper plugin. We can use it to measure the FPS of the JS and UI threads in debug builds. Make sure to turn off the dev mode when profiling. Your app works faster, displays complex data structure, and you opt in for further improvements. Thanks to using specialized component, your application will always run as fast as possible. You can automatically opt in to all the performance optimization performed by React Native and subscribe for further updates. At the same time, you can also save yourself a lot of time re-implementing the most common UI patterns from the ground up. Sticky section headers, pull to refresh, you name it. These are already supported by default if you choose to go with flash list. Think twice before you pick an external library. So we will start with this in the next video. Thank you for watching. Bye.